Hello. In this video, we're going to exemplify solving homogeneous differential equations. So recall that the homogeneous first order ordinary differential equation has the form dy over dx equals f of the variable y over x. Our method of solution consists of making the substitution y over x is the variable v. We find dy dx by cross multiplying, so you have v, y equals y over x, in which case y equals x times a v. When you differentiate, applying the product rule, you obtain that dy dx equals to 1 times v plus x times dv dx, or simply dy dx equals v plus x times dv dx. So that makes our equation dy dx equals f of y over x become a left-hand side dy dx is v plus x dv dx from our finding equals f of v. When you look at the resulting equation, you realize that it does happen to be a separable equation. So as such, you separate the variables. You obtain dv over f of v minus v equals dx over x. Let's carry out these steps here on the camera. So you have v plus x dv dx equals to f of a v. So we are going to show the separation. So first we subtract v on both sides. So we end up with x dv dx equals f of v minus v. The separation consists of dividing both sides by f of v minus v. And at the same time by cross multiplying dx and dividing by x. So when we cross multiply dx, we end up with x dv over f of v minus v equals dx, and lastly divide both sides by x, divide by x, divide by x. And there are your variables. On the left side, you have v. On the right side, you have x. So thus, we can solve this resulting equation as a separable equation. Let's simplify. Solve the given homogeneous ordinary differential equation. In number 1, solve dy dx equals to tangent of y over x plus y over x. So our substitution is a v equals y over x. Remember that consequently, when you cross multiply and you get dy dx, you obtain v plus x dv dx. So we're going to make the substitution. Y over x is replaced by v. dy over dx is replaced by v plus x dvx. v plus x times dv dx equals to tangent of v plus v. Observe that we get some algebraic simplification here. So we end up with x dv dx equals tangent of v. Now our separation here is immediate. Divide both sides by tangent of v. So you get dv over tangent of v. And then multiplying, cross multiplying dx dividing by x. So we obtain dx over x. Now we integrate both sides. On the right side, we get the natural logarithm absolute value of x plus some constant. I'm going to call it c1. On the left side, if we rewrite 1 over tangent of v as a cosine of v over sine of v, we end up with a rather simple integral. So observe that the denominator is sine of v, the numerator is d of sine of v. Because when you differentiate sine, you get cosine. So what is the integral of the differential of sine of v over sine of v? That is the natural logarithm of the absolute value of sine of v. And that equals, on the right side, we had ln of x plus c1. We can drop the natural logarithms. There is a technicality here. We say this: e to the left side equals e to the right side. On the left side, you end up with sine of v. Disregarding the signs, we're going to relax the signs here. Could be plus, it could be minus. We're just going to call it sine of v. On the right side, observe that when you split this up, you get e to the ln x, e to the c1. So this becomes e to the ln of absolute value of x, e to the c1. This I can call c. It's a constant. E to the ln of absolute value of x is x, absolute value of x, but we're going to relax the sign here. That can be absorbed into the constant. Okay, so we have solved our equation. One last detail. Our given equation, our given differential equation involves the variables x and y, so I should back substitute, replace v back by y over x. And then do the corresponding algebra. You want to solve for y, then you do the algebra that allows you to solve for y. So here I could take an inverse sign on both sides, so I get y over x equals the inverse sine of x times cx, or I could just say cx. You want to solve for y, cross multiply the x, so you end up with y equals to x inverse sine of c times x. Okay, so that's our first example. Second example, dy dx equals x squared plus y squared over 2x squared. Now, our example says solve the given homogeneous equation. We have to put it in the proper format. I'm being told that this is a homogeneous equation, but it isn't in the format that I need it to be. I need a homogeneous equation to have dy dx equals to some function depending on the variable y over x. So it is just a matter of achieving that form. So all I have to do to make the right side be dependent on the variable y over x, all I have to do is divide top and bottom by x squared. So let's do that. So we have dy dx equals to x squared plus y squared over 2x squared. Divide the numerator and denominator by x squared. So we end up with x squared over x squared is 1 plus y squared over x squared is simply y over x to the second power. In the denominator we have 2. Now we have confirmed that this given equation is indeed homogeneous. So our substitution, v equals y over x. We need dy dx, which we know it's v plus x dv dx. So dy dx gets substituted, v plus x dv dx. That equals 1 plus v squared over 2. 1 plus v squared over 2. Now our next step is to separate the variables. So let's begin by moving v away to the right side. So subtract v on both sides. Observe that we can place this as a single fraction if you just write the fraction with denominator 2. So we end up with x dv dx equals to, denominator is 2. Let me rearrange my terms in decreasing order of exponent on the variable v. So I get v squared minus 2v plus 1, which is a nice expression. It factors into a perfect square, v minus 1 squared. That makes the problem manageable. Now our separation of variables is next. So let's multiply both sides by 2 to get rid of this half. Let's also divide both sides by v minus 1 squared. v minus 1 squared. v minus 1 squared. So what do we get? Well, we get 2x dv, 2x dv over v minus 1 squared. Let's also cross multiply x right away, dx, sorry. So on the right side we have 1, but then when we cross multiply dx, we just get dx. Only thing we need to do is get rid of the x, so multiply by 1 over x on both sides. So cancel, cancel. So the separation of variables is complete. So what do we have now? We have 2 dv over v minus 1 squared equals dx over x. So now to solve, we integrate on both sides. On the right side, we get the usual, which is the natural logarithm of absolute value of x plus some constant. I'm going to call it C1. On the left side, if you put the 2 outside and then apply the power rule for integrals, you see the integral that we are dealing with here is a v minus 1 to the negative 2 dv. So you end up with increase the power gives you a negative 1. So this is v minus 1 to the negative 1 over the new exponent, which is negative 1. So increase the power, divide by the new exponent. So at the end, we have negative 2 over v minus 1 equals to the natural logarithm of absolute value of x. Now, let me rewrite this as the natural logarithm of e to the c1. When I do that, I can absorb e to the c1 into this logarithm, but furthermore, that's just a constant. So we're going to call it just plain old constant c. Minor algebra. Let me multiply top and bottom by negative 1. little bit of algebra there. So you get 2 over 1 minus v equals to the natural logarithm of, I could drop the absolute value if I were to absorb the sign on the constant. So let me say this in here. Let me go back and just say that there is a parenthesis there. So I get cx here. Okay, so we solved our resulting separable equation. Last step now is to retrieve back the original variables. Remember that v is y over x. So this left-hand side is 2 over 1 minus y over x, and that equals ln of cx. Okay, so that completes the solution to the second equation. Now what's left is the algebra. If you would like to express your answer where y is solved for, then you have to multiply top and bottom by x. So that will give you 2x over x minus y equals ln of cx. One or two more algebraic steps and you will obtain your final result. I'm going to copy it here from the notes. I will show this from the notes. But here is would be your final answer if you are solving for y. Y equals x minus 2x over ln of cx. Okay, so there you are. We have presented a couple of examples. Let me show you the notes. So here are our solutions in summary. This is what we did for our first solution. And then our second solution, we went through the process of verifying that our equation was homogeneous. We made our substitutions. We obtained our separable equation. We solved it as usual by integrating both sides. We got our partial result, partial solution. Okay, we made our back substitution. And after our back substitution, some algebra gave us this final answer. Okay, that's all for now. Thank you.